Okay, so the recording has started. We can begin. But before we begin, do we have any questions or suggestions? Do we have any questions in advance? Any? Okay, so if there are no questions, we can go straight to the business of the day, which is looking at TSF. In TSF, all what it is transforms. So if you, at a high level, not if you, but at a high level, all what we are doing TSF for is for solving differential equations. That's what we'd use it for. So I think that before you start the course, it is important that you note that the reason why we are doing TSF is in part because we want to use it to solve differential equations. It makes life to be easy. So let's note that down. But one of the reasons why we are doing TSF is because we just want to solve differential equations. And TSF gives us the tools which we can use to solve differential equations much more simpler than we actually do when we use calculus. So you'll be able to see, so you'll be able to compare how you solve a differential equation on the calculus course and also how you solve a differential equation on the TSF course. So you'll actually see that when we do TSF, it actually becomes easy. And TSF in general is easy. So let's go straight to the business of the day. So we are looking at your TSF, and AKA they call it transform. And the question is, why are we even doing it? And the answer is simple. All what we want to do is we want to be able to solve differential equations. Let me say, yeah, that's all what we are using this TSF for. We just want to solve differential equation. And what your TSF entails is actually integration. So first year is coming back and it's catching up, because for your TSF, what you need is your knowledge of integration. So that's one of the things which you need. And what we will look at is what we call improper integrals. So let's note that down and see what are improper integrals and how can we deal with them. So all what improper integrals are is, if you remember your definite integral, let's say we are integrating a function. Let's call it f of x dx. And we are integrating this between a and b. If the integral of f of x is capital letter f of x, then we know that the integration can be evaluated as such because it is a definite integral. And this equals to, at the end of the day, f of b minus f of a. This should ring bells from first year. But now with proper integrals, the problem we face is we usually have the a, or let's say the b. We usually have the a or b equaling to plus or minus infinity. That is what makes it to be an improper integral. So one of the limit is very strange. It can go to infinity, positive or negative infinity. Are we still together? Okay, so let's work this out and see if it really makes sense, because as we speak, probably someone is saying this doesn't make sense, right? So your Laplace transforms, which is what we are focusing on, because we said this course is transforms, so meaning there's many transforms. There is Fourier transform, but the first part of the course is going to focus on what they call Laplace transform. And Laplace transform, we denote it using the sign, it's a funny L, f of t. So all what this means is we are taking the Laplace transform of f of t. That is what this notation means. We are taking the Laplace transform of f of t. And notation-wise, if we take the Laplace transform of f of t, small letter f of t, the answer becomes capital letter F, but now the dependent variable, the independent variable now becomes S instead of t. This is what we call our Laplace transform. So we have transformed our function f of t to be f of s. And if you look carefully, we moved from the input was time. So that is what we are going to call the time domain. And our final answer now has capital letter with an input which is S. And this is what we now call, we have transitioned to the frequency domain. Okay, so it's just the basic terminology which you need to be aware of. Obviously, you're not going to get assessed, but it really helps for you to know what exactly you are doing. So when you're taking the Laplace transform, we are transforming a function from the time domain to the frequency domain. That's what we are doing. So let's look at the definition, because we said when we deal with transforms, actually what we are doing is integration. So let's see how the integration comes into play here. So if they are saying take, let's put it in quote. If they're saying take the Laplace transform of f of t, all what this means is we go here, we put f of t. And with what we did, we know that the answer should be f, capital letter F of S. But there's a way we define the integral which describes the transformation. And the integral is given by, we integrate from 0 to infinity. We have e to the negative st, and then we have f of t dt. So which means if you are looking for the Laplace transform of a certain function, all what you do is you integrate that function multiplied by e to the power of negative st integrated from 0 to infinity. This is the definition of the Laplace transform operation. So this you definitely need to know the same way you know your name, because this is all what Laplace transform is. All the shortcuts or the equations which you are going to use, they all come from this integral. And obviously, what we are looking at now should ring bells. You are multiplying one function which is dependent on t. There's the t. Another function which is dependent on t. There's the t. So you now have, you are trying to integrate a product of two functions, and this would ring bells. That what do we do when we integrate a product of two functions? If you remember from first year, if you are integrating a product of two functions, it should ring in your head that you should be familiar with what rule. Anyone? If you're integrating a product of two functions, which rule should you be familiar with in order for you to do the integration?
I think it's integration by parts, sir.
Yep, agreed. So if you're integrating the product of two functions, your head should ring integration by parts. So which means in part, what you need to look at is how do we do integration by parts? So let's note that down. So you should ring integration by parts. And if you recall, integration by parts, all what it is if we have the integral of two functions, and those functions are u and dv, the answer is simply uv minus, sorry, v du. This is what the answer is equal to. This is what we call for integration by parts. So as a heads up, you should, when you look at this document later, revise this. So it should be in red. So you need to go and look at your integration by parts. If you can do integration by parts, it makes your life to be very easy. Okay. And then let's scroll down and then give this. Let's give an example, a short. So let's say we are given f of t. Let's take the first example. So let's say f of t is e to the alpha t. And when you look at past papers, which you will in a few weeks' time, is that at times they say find the Laplace transform of a function, and they say do not, and they say using okay, my network is bad. So I'm saying if you look at past papers, you will realize that at some point they usually say that find the Laplace transform of a certain function by integration, but it hardly comes out that way. It's just the question which will hardly come out, but it can come out. So let's see how we can find the Laplace transform of this function. So let's put the question here. So the question is find which all of this means is the Laplace transform of f of t. So that's what we need to find. So we go up here, and this you should know by your head at least before you open next week. It's just a simple integration. So for us to find the Laplace transform of f of t, we need to integrate from 0 to infinity. We will take e to the negative st and multiply it by the f of t, which is our function, and integrate with respect to t. So with that in mind, let's come here and see we can do that. So f of the Laplace transform of f of t is equal to the integral from 0 to infinity e to the negative st times our f of t is e to the alpha t dt. High school maths, same base, we are multiplying the two, so the exponents should add up. So that means we have e to the power of alpha minus s, and then the t is outside, and then we have dt. Okay, so now we need to integrate that part. So someone, can they please give me the answer? What is the integral of e to the power of something times t? Okay, let's pause. So we should all be able to integrate something like, let's say, bx dx. It's the same thing. So I'll pause and wait for the answer until someone gives us the answer. We will not continue. What is that integral?
Hi, sir.
Yes.
Can you hear me?
Yep, I can, loud and clear.
Oh, okay. So what I get as an answer if I integrate, I think when integrating e to the power of alpha minus s t dt, right?
Mm-hmm.
So my answer if I integrate that, it will be e to the power of in bracket alpha minus s bracket t all over the constant there, which is bracket alpha minus s, and then two huge brackets for the limits of integration, which is 0 and infinity.
Do you mean like this?
Yeah, sorry, muted.
Okay, so this is what you were saying, which I wrote.
Yeah, that.
Okay, cool. And then someone please give us. Mhm. Okay, and then from here, what do we do? Someone else, what do we do from here? I'm avoiding pointing fingers. We are here. What do we do from
Can
here?
I
This is
answer?
evaluating. Yes.
Okay, from there you're gonna insert your limit of integration. So on t. So instead of t, there you're gonna write like infinity. So you write your whole e to the power of alpha minus s in bracket and then t outside over alpha minus s, and then minus, now you write like the lower limit, it will be e to the power of bracket alpha minus s bracket and then 0 outside and then alpha minus s.
Okay, this is what you are saying. Okay, guys, and what do we do from here? Okay, am I cutting or we are still here? Mobile, can you hear me?
Yeah, again.
Okay, so is it my network or it's her network which is a problem? That's what I'm trying to figure out.
I am not sure whose network is the problem.
But were you able to hear her loud and clear?
Yes, I was.
Okay, so on my side, I was not able to. But let's see, let's quickly conclude this problem. So what's going on is this part is gonna be 0. So let me copy this to the next page to avoid any confusion. But this is good as done. So remember that we are dealing with improper integrals. So we are avoiding the integral blowing up to infinity. So what's happening here is the real part of S, which is what we are focusing on. It should always be greater than your alpha. So if that's the case, then if you think carefully, this exponent here is actually negative. And if you remember from first year, if you remember the limit of, let's say, x as it approaches infinity of e to the negative x, this will just be 0. It will tend to 0. So that means the first part of the integration actually tends to 0. So we have 0 over alpha minus s. The second part, the numerator is simply 1, because what we get is e to the 0, and then divided by alpha minus s. So if you look at this carefully, what you have is actually it's the final answer. If you remove that negative or multiply the denominator by a negative and the numerator by a negative, what you get is simply 1 over s minus alpha. So which means the Laplace transform of e to the alpha t is actually 1 over s minus alpha. So which then means, now if you go to the course and you find yourself in a position where you need to find the Laplace transform of e to the 4t, this means your answer is simply 1 over s minus 4. And this also means if you find yourself in a position where you need to find the Laplace transform of this function, then we can see that the alpha is -1. So it would be 1 minus s minus alpha, which is -1, so it should be positive. 1. Right, so we now see that, look, this has now become more of a rule, but we actually had to do it manually. But in the future, we now know that if we're looking for the Laplace transform of e to the power of something times t, it is just 1 over s minus the something. Okay, are we on the same page? Do we understand?
I have a question.
Yep.
How do we know that the real of s is actually greater than the lambda? I mean, the alpha.
Yes, so here's what's happening. We are looking at improper integrals, and what we are trying to do at the end of the day, is to find value when integrating. So if this is not the case, then if this becomes positive, let's say it just becomes e to the something which is positive. Let's put it like this, and then you put infinity. This becomes infinity, and your entire integral, if you minus infinity or you divide infinity by something, the answer will still be infinity. So it defeats the purpose, meaning for us to be able to utilize Laplace transform, we need to make sure we impose this condition. Because otherwise, if we do not, we'll face such a case and we'll be having integration which equate to infinity, and infinity is not defined, as you know. We cannot define infinity to a not a discrete value, but we can quantify infinity. So for us to be able to utilize Laplace transform, we need to put a restriction. And then we'll always work under this restriction, because if we put another restriction, it then lands us in this position, which then has no meaning. It's not useful in any way. If you integrate something and you find infinity, what's your interpretation of that integration? It's like, let's say you are trying to find the area or the power by integrating and finding the area under a curve. If you find infinity, how do we define a power which is infinity? It doesn't make sense. So we need to impose that condition for us to have workable results. Does this answer your question?
Yes, it does.
Okay. So let's see. Here's the takeaway. This is the first Laplace transform equation, which you should know by head, is that the Laplace transform of e to the alpha t is 1 over s minus alpha. This you should know. The same way you know a lot of things. It should be one of the lot of things from now on. So there's many equations which we can derive, but we are not going to spend time deriving them because you need to know them by your head. Right? We can take one of them and see how we get to it, but I am gonna give you the equations and then we'll use them. So this one we did derive, so it's number 1. So let's label it as number 1. And then let's see number 2. So I'll write them down and then we quickly jump to the third questions and you see how we apply these rules to solve the problems which are given. But remember that the bigger goal at the end of the day is to be able to solve a differential equation using Laplace transform. So to not be lost in the process, the aim is to be able to solve a differential equation using your Laplace transform. That's the end goal of the course. So you should keep that in mind. And the question which may arise is, why should we even solve differential equations? And the answer is simple. It's because differential equations, they appear everywhere. They even appear in circuits when you interpret them. So let's look at a quick example and then we'll bounce back to this, because there are people who have difficulties doing something, not understanding why they're even doing it. Right. So let's consider a circuit. Let's name this page some, let's say, background. Because doing the maths is easy, but knowing why we are doing the maths makes it to be even easier, because you will eventually do it. So let's consider a simple circuit where we have the power source and we have a resistor. And let's see, we have an inductor and we have a capacitor. And then we have plus or minus. So the source, let's call it x of t. Here we have R for the resistor, we have L for the inductor, we have C for the capacitance. And we have current I flowing here. And across the terminals of the capacitor, or across the capacitor, we are measuring a voltage. Let's call it Y of t. And now the question is, we now need to analyze the circuit and figure out what is going on. So let me quickly give you some context. So when we are looking at a resistor, so what we are looking at is, let me come here and say, we are looking at current and voltage relationships. Well, let me say relationship. It's that. So when we are looking at a resistor, you should know Ohm's law from high school. How is current related to the voltage across the resistor? So if you remember, V for a resistor is simply IR. And if we look at an inductor, how is the voltage related to the current? The current across an inductor is given by the inductance times the derivative of the voltage with respect to t. So we already have derivatives now, which means maybe a differential equation will pop up, but let's see. And then we're looking at a capacitor. And the question is, how is voltage and current, how are they related in a capacitor? And it is simple. Voltage across a capacitor is 1 over the capacitance multiplied by the integral of the current with respect to time. So here what we have is the relationship between the voltage and the current for a resistor, an inductor, and a capacitor. Okay. So let's see if we can now construct an equation out of these. So let's look at this circuit. So we know that these components are connected in series. So for components which are connected in series, you should remember from high school, what is the same? It's a question, good people. Click that unmute and answer the question. We have components which are connected in series. What is the same?
It is the current.
Okay, great. It is the current which is the same. So, and we know from high school that when we look at this circuit, it's actually simple. But now it's coming up at verts because it's verts. It appears like it's complicated. So the source voltage, which we are providing, X of t, it should be equal to, so meaning the voltage we are putting in the circuit should be the voltage which is in the circuit. We are not expecting more than what we put in. So the voltage we put in, X of t, should be equal to the voltage across the resistor, which we will call VR, plus it should also be the voltage across the inductor, which we will call VL, and plus the voltage across the capacitor. And this should make common sense. Look, we are supplying the circuit with a certain voltage. When we sum the voltage, which is on the resistor, the inductance, and the capacitance, it should give us the voltage which we're providing, which is X of t. Right? Nothing scary. And what we now need to do is to say, how can we express the voltage across a resistor and put it here? How can we express the voltage across a capacitor and put it here? That's what we are trying to find out now. How can we put in these here? So what should we do? Anyone? What should we do? So the voltage across a resistor we have, let me see. Okay, catch. Please be wary of this. The voltage across an inductor is the derivative of the current. Yep. So that's a silly one there. My apologies. So let's see now if we can make a differential equation out of this. So X of t is equal to VR. The voltage across the resistor, we know it is I times R. The voltage across the inductor, we know it is L di dt, plus the voltage across a capacitor, we can see it is 1 over C times the integral of I dt. Now, this looks like a differential equation. The only difference is we now have an integral. And how you remove an integral is by differentiating. So which means now what we need to do is to differentiate the left-hand side and also the right-hand side. And the reason is simple. We do not want integrals here. So we'd rather have derivatives, which now becomes a differential equation. So we'll remove this integral here by deriving the left-hand side and the right-hand side. And you know, when you integrate and derive, it's more like you are doing nothing. So that's how we remove the integral sign. So let's copy this to the next page and see that, look, our easy circuit turned out to be a differential equation. Let's paste here. So now if we differentiate the left-hand side and the right-hand side, the left-hand side will have dx of t dt equal to, now we'll have r di dt, because we are differentiating with respect to t, because there we're integrating with respect to t, plus now we have L, we had already the first derivative and we are deriving again, so it should be the second derivative. And then plus 1 over c times I. When you now differentiate, the integral disappears and you are left with that. So if you look carefully, all what we have here is simply a differential equation. It is L d squared I dt squared plus R di dt plus I over C, and this is just dx dt. And this is what we call a differential equation. Should look familiar. This is just the second order differential equation. Why differential? Because we have a lot of these dt's, these dt's. The equation is in terms of those. So this is a differential equation. So can you now see that with the differential equation, if you remember, from the calculus session, when we had something like, let's say, d squared y dt squared plus, let me say, 3 dy dt. Here, let me put 2y, and let's say this is equal to sine t. So remember that the aim, we would say, it is typically to solve for this. You solve for whatever variable of interest. So here it would be just, we need to solve for y. But now, from our differential equation here, we can clearly see that we can actually solve for I, our current. So we can solve for the current from that differential equation. And that's where Laplace transform comes into place. Instead of doing it the tedious way which we use when we do actual calculus, with Laplace transform, your differential simply becomes a product of some polynomial of S and the capital letter of that letter with the input S. Okay, so let's not stress about that, but the point which I was trying to get across is that we use Laplace transform to solve differential equation. And the question is, why would we make up differential equations and then try to solve them using Laplace transform? And the takeaway is, we don't make differential equations. They make themselves. You come across a circuit and you are like, look, I am trying to find out what is the current which is flowing on this capacitor. And it's not easy to find out. And then you start creating your equations here. And then they push you here. And then they push you to a differential equation, which you now need to solve to find your I. So we don't make problems so that we can solve them, but we use the tools which we have to solve these problems. Any question? Okay, so if there are no questions, then let's move on. So now I hope it makes sense why you need to learn Laplace transform. You will need to solve differential equations and they will come up from your circuits. You'll have a circuit there. When you see a circuit, you should be able to build the differential equation on paper, solve it on paper, figure out how the current behaves. Then when you now know how the current behaves on paper, you go and take your oscilloscope and you measure and see if you get the behavior which you are getting on paper. And if you are getting it, then thumbs up. If you are not getting that behavior, you need to explain why do you think what you are getting on paper and what you are measuring does not correlate. And that's where engineering starts. Okay, let's fast track back and let me give you the equations, which I said you should know by heart. And then let's see if we can work out a few third questions. So let me write here. Let me say must know So when you look at this later, you must know that this is a must know. So the first thing which you must know, number one, is that the Laplace transform of e to the alpha t, which we did prove, it is simply 1 over s minus alpha. Number two, what you need to know is that the Laplace transform of e to the alpha t cos of bt is equal to s minus alpha over, s minus alpha squared plus b squared. This you must know. 3, the Laplace transform of e to the alpha t sine of bt, this should be equal to b over s minus alpha squared plus b squared. Then another one which you need to know, number 4, is that the Laplace transform of t to the n is equal to n factorial over s to the power of n plus 1. And here where n is 0, 1, 2 going up. So essentially n is an element of natural numbers. And then let's look at number 5 and pause here. Laplace transform of e to the alpha t times t to the n is the same as n factorial divided by s minus alpha to the power of n plus 1. Okay, so these, let's leave them as a must know. In fact, you will be given a table of these when you write, if I remember well. But the table is meaningless if you don't know how to use it. So if you can memorize these, then for sure you should do so. But you don't even need to memorize them. The more you use them, the more you easily remember them. So let's look at a few examples and see how we apply this. So on these examples, it's clearly stated that use the formula. So you are not integrating, but you are using the formulas which are already given. So let me say you are not integrating. So the first question is A. So we are find the Laplace transform of the following. So for A, what we have is our f of t is e to the 2t. So now we are looking for the Laplace transform of e to the 2t. So you should look up and say, look, what is the Laplace transform of e to the alpha t? It is simply 1 over s minus alpha. So we scroll down, we can see that the alpha is 2 there. So we can see that our alpha is 2. So therefore, our answer is 1 over s minus alpha, which is 2. And we are done. Let's look at B. F of t is e to the negative t. And here I should be able to look at number 1. Say, okay, so I'm looking at number 1. I can see that my alpha is actually negative 1. So therefore, the answer here is equal to 1 over, I know it is s minus alpha. So we have s minus 1 becomes s plus 1. And there they go. there's their Laplace transform. Okay, let's go to another one. So let me give you, let me give you number 6 here. 5, let me give you number 6. For number 6, let me just say the Laplace transform of cos bt is just s over s squared plus b squared. Number 7, the Laplace transform of sine bt, that is b over s squared plus b squared. And then 8, the Laplace transform of hyperbolic cosec of b bt is s over s squared minus b squared. And then the last one, let's name it number 9, which is the Laplace transform of hyperbolic sine of b t. And this should just be b over s squared minus b squared. So let's keep these in mind. Let me copy them to the next page and see if we can answer more examples. Remember, the end goal is either you should know these or you'll use the table. But my suggestion is try to know these. They are not hard to memorize. So let's look at another example, which we will call C. And for C, our f of t is hyperbolic cosine of 2t. So we are looking for the Laplace transform of that, which is that funny L. Then we have our hyperbolic cosine of 2t. So if you look at your formula, it is simply s over s squared minus b squared. So we can see that actually our b is just a 2. So Laplace transform of hyperbolic cosine of bt is simply s over s squared minus b squared, which is 2 squared. So our answer is s over s squared minus 4. Let's look at D. For D, they gave us f of t is equal to cos t. So I can see that my b is 1 when I look at this one. Can see that my b is 1. And now I'm looking for the Laplace transform of cos of bt, where b is 1. So this should equal to s over s squared plus 1 squared, which is just s over s squared plus 1. That's the Laplace transform of your cosine. Any questions here? Any questions, guys? There are no questions. Let's carry on and look at another example, E. So let's say you have a case where now your f of t looks much more interesting than the other ones. It is actually sine of t plus pi over 3. So this is more interesting. And one of the easy ways you can work this out is because we can see that we don't have, here's our sign. We only know the Laplace transform of sine pt. We don't know when it's plus something. So let's look at that sign and break it down. So high school ratios. So this should be sine of t, then cos of pi over 3 plus sine of pi over 3, and then cos of t. Right, so sine of t okay, sorry, that was my network. So what is cos of pi over 3? Anyone? Special triangles. What is cos of pi over 3?
How
Can you repeat?
half.
And what is sine of pi over 3?
Root 3 over 2.
Okay, and this is our good sine of t plus pi over 3. And guess what? We are looking for the Laplace transform of sine of t as pi over 3. So which means we can actually take the Laplace transform of the left-hand side. So we have a half here. It is a constant. So you can pull it out. And what you do on the right, you do on the left-hand side. So Laplace transform of sine of t plus, it's a constant. And pull it out and take the Laplace transform of cos of t. So if we quickly look at, zoom out and look at our table or our equations. So we should have a half times Laplace transform of sine pt. The b is 1 there, so it's going to be 1 over s squared plus 1 squared plus square root 3 over 2 times cos of bt. It is s over s squared plus 1 squared. So essentially our answer, when we combine it, we can see the denominator is common. So all what we have is we can factor out the 1 over 2 and inside have 1 over s squared plus 1 plus square root 3 s over s squared plus 1. And common denominator, we can group these and have 1 over 2 into 1 plus square root 3 s over s squared plus 1. And there we go. That's our good Laplace transform. So we know the table, but we couldn't figure out. The plus was complicating life, but we just had to use high school knowledge. Sine of alpha plus beta is sine of alpha cos beta plus sine of beta cos alpha. Right. And then let's look at another one. So now let's say they say find the Laplace transform. This would be f. If they now give you e to the 2t sine of t. So essentially what you have here is e to the alpha t sine of bt. That's what you technically have. And let's see the Laplace transform of this. Let's go to the previous page. So Laplace transform of e to the alpha t times sine bt. So it's simply b divided by s minus alpha squared plus b squared. Okay, so that means here we can see that our b is 1. So we have 1 over s minus our alpha, we can see it is 2. We square it plus 1 squared. So this is our answer. 1 over s minus 2 squared plus 1. If you like, you can expand that. I don't know why you would want to do that, but you can. And this simply becomes this. And that's your Laplace transform of that function. So you can apply it to many functions which look very weird, but we can be able to solve them. So let me give you G, and for G, I'll leave it as homework. Okay, so there we go. There's our f of t, and your homework is for you to find the Laplace transform of f of t. And you also have a homework to find, let's say this is number 1, G. This is number 1. Number 2, you need to find the Laplace transform if f of t is t plus 1 cubed. So someone else can choose to expand this, and you can easily expand it using Pascal's triangle. Or you can do FOIL. Maybe there's no need for you to expand it. Maybe there's a simpler way. So go and figure this out, and let's see what you obtain. And another one which you should do is t times e to the negative t. And number 4, which is the last one, you go and deal with t e to the t sine of t and share these in the group. Okay. Right. So what we were doing here is actually, if you remember, we have f of t, because we said the ultimate goal is to solve differential equations. And you just transform to f of s. So this is Laplace transform. And then at some point, you will need to reverse back to f of t. And this is now what we call the inverse Laplace transform. Because remember, we said the aim is to solve differential equations. And when we take the Laplace transform, it becomes easy to solve the differential equation. But when you now solve it, it will be in terms of s. But the original expression was in terms of t. So which means we now need to find a way to reverse the effect of the S by using inverse Laplace transform back to T. So look at this carefully. We moved from the time domain to the frequency domain. And then we solve. So let's say here, we just solve this stage. Then after solving, we need to be able to go back to the time domain because our problem was presented in the time domain. So this is essentially what you will be working towards. You will do Laplace transform, switch to the frequency domain, solve the problem because it's easier when you do it in the frequency domain. After you are done solving the problem, we now need to stress about how do we go back to the time domain? And this is where your inverse Laplace transform comes into place. And this you should be able to get more insight on when you kickstart the course. But for now, let's pause here and see if there are any questions. But while I wait for questions, let me delete my pages. If there are no questions, we can call it a good day. Okay, any questions, guys? Okay, if there are no questions, we can call it a day. And the next session will be doing more problems because the aim of the session is not to make you to do a lot of problems. You should get a good understanding of the course and you should be able to start reading from what we have done. It shouldn't be as scary. So if there are no questions, we can call it a day. I'll share the recording and what I was writing. So cheers and thanks for attending.